Okay, guys, it's time. Let's go. We return to the problem of computing magnetic flux. Start this morning with this problem. We have to find here the magnetic flux inside a Gaussian cable. Okay. Last time we found that inside this Gaussian cable there is an MF like this. And let me remind you that the direction of this field is something like this. Okay, it goes around the inner cylinder, and so you can see that this magnetic flux passes through an area like this. This area is alongside the common axis of the system. Now we have to find the total magnetic flux flowing through this rectangle, for example. So firstly, if you want to find the magnetic flux, we have to know the density, okay? And finding density from MF5 is very simple. All we have to do is to multiply this one to mu0. That's it. For the magnetic flux, we of course have to rely on the definition. I mean its definition. Here you are. It is a surface integration of B dot ds. ds, the very small area of this rectangle, can be found from this formula. I told you about this several times. Okay, and then there you are. You make the dot product between the given B and just found ds. Please notice that A5 dot A5 is 1, and finally got this. I think that this integration is not very complicated because this only variable is rho, and the primitive function of 1 over rho is a natural logarithm of rho, and we got this. The magnetic flux here is proportional to the current and to the length of the Gaussian cable. There you are. So, do you guys have any question for this? Okay, keep going. The next one. We are given here a current and a frame. The current here, you know, produces an MF5, a magnetic flux, and we have to find the total magnetic flux flowing through this frame, this rectangular frame. The frame and the current here are on the same surface, which is your screen. The dimension and the position of this frame are given, as you can see here. So to find the magnetic flux, we once again rely on its definition. And for a second time this morning, we use the result that we found several times ago. This is a magnetic, this is the MF5 created by a straight line carrying a DC current I. To find ds here, we can divide the frame here into many very narrow rectangles, as you can see here. The length of this rectangle is L. The width of this rectangle is d rho, and d rho, you know, is very, very small, so we can think that this one is a very narrow rectangle. Okay, so for this very small rectangle, its area will be L times d rho, and its direction will be tangential to the MF5, which is A5. Then we got this. And I think everything will be fine right now. You find the dot product between B and ds. A5 dot A5 is 1. And to cover the whole rectangle here, we have to move the thin rectangle here from the left to the right. And during that movement, the variable here is the distance from the thin rectangle to the current, and that distance is rho. So rho you see is, rho here varies from A to B, and we put the two ends into this integration, as you can see here. There you are. And I think you can find by yourself this very simple result. We take a look at this result. The magnetic flux here will be, firstly, it is proportional to the current once again, and to the length of the frame. The magnetic flux here will be 0 in 4 cases. Firstly, if there is no current, so there is no MF5, and therefore there is no magnetic flux, obviously. Secondly, phi here will be 0 if n is 0, meaning that there is no frame. Okay, because in that case the frame here will be a straight line. And phi here will be also 0 if B and A are the same. In that case, once again, we didn't have a frame. And finally, in that case, you see that when B and A are the same, so this one will be natural logarithm of 1, which is 0. And finally, if B and A are very, very large, so the magnetic flux will be 0. Mathematically, if B and A are very, very large, so B over A will be 1, and natural logarithm of 1 is once again 0. And physically, if B and A are very large, it means that the frame here is at infinity. And at infinity, there is no MFI. And therefore, there is no magnetic flux. Are you okay? All right, for this example, we have, instead of one current, we have two currents, IA and I2. Okay. Now, firstly, we have to use the right hand to determine the magnetic flux, to determine MFI created by the two currents here. You can see that in the region between the two currents, both MFIs enter the surface. They go from the front to the back of the screen, as you can see here. So, because the two MFIs here are the same direction, so when we synthesize them, we can add them together. Okay. So, by definition, we have we have the magnetic flux like this, and like I told you, the total B here will be the summation of B1 and B2. B1, we knew this a long time ago, and we also knew B2. But please keep in mind that for B2, rho here must be the distance from the given point to the source of MF5, and the distance from here to the blue current will be C minus rho, like this. Once again, like the previous example, ds can be computed like this expression. Okay, and there you are. Once again, this integration is not very complicated, so we can come to this. So once again, you can see that the magnetic flux here is proportional to the two currents, I1 and I2. Are you okay? Any question?
So how we find that ds?
Sorry?
How to find ds?
ds is the area of this very thin rectangle. The area of this rectangle will be the length, which is L, multiplied to the width, which is 0. Okay, I told you about this in the previous example.
But why it depends on arrow, AV?
A5, because look at this. I will try to draw in 3D figure. This is the MF5 created by the current I1. Okay, this is the MF5, and A5 is a tangent to the circle, meaning that it is perpendicular to the radius. This one is A5. There we are. So in this case, we are here. We are on this surface. So the direction of ds is perpendicular to the surface, and this one is the ds. And being perpendicular to the surface of the frame here is A5.
Thank you, sir.
Never mind. Any other question? Okay, so I want you, if there is no further question, I want you to do the first mid-class exercise this morning. I change the direction of I2. In this exercise, I1 and I2 are on the surface of the screen. Now I change the direction of I2. This is a new direction of I2. I2 enters the screen. Are you okay? And therefore, I2 is perpendicular to I1 and also to the frame. Please redo this exercise. You understand the question? Okay, I give you 5 minutes. Go ahead, please. Are you done? Okay, keep moving. In the previous example, we worked on a rectangular frame. Now it is a triangular one. We got here a current and a triangular frame. The position and dimension of this one were given, as you can see on the screen. So the question is the same, to find the magnetic flux flowing through this frame. Okay, this is the direction of MFI. So the problem here is to try to find the ds, the very small area. So in this case, I divide this one into many very small, so how can I say, very thin trapezoid like this. Okay, this figure is very thin. Its position is rho, and its thickness is d rho. Because d rho is very small, so we can think that. Give me 1 minute. We can think that this trapezoid is can be regarded, can be considered as a triangle. Sorry, as a rectangle. Okay. Are you right? We had to find this. We had to do this because according to the definition, we had to find the s. Firstly, like usual, this one is the expression of MFI. And for the s, the area of this figure, of this set, will be the length multiplied to the width. The width here is 0, and the average length of this trapezium is L. And the direction of this one is A5 because A5 is perpendicular to the screen. Now we have to find L rho, and here obviously depends on rho. So how can we find L rho? In this figure, in this system, you see that we have two triangles, the small triangles and the big triangles. They are similar. Do you see that? So this edge over this edge will be the height over the height, and we have this. This equation here came from two similar triangles, the small one and the big one. Are you right? From this, we can find this function n rho. To check the how can I say, to verify this result, we can see that if this one is at the bottom of a triangle, and here must be h. So when the trapezium here is on the edge here, rho will be a. And when rho is a, you can see that and here is h. And secondly, if this figure is on the top, on the peak of a triangle, n must be 0, and in that case rho must be b. And if you take a look at this, you can see that when rho is b, and here is 0. By using those two checks, I can believe that my result here is correct. All right, so now I put this one into this, and it combine all of them into the definition of magnetic flux. You have this one. Very well. Are you okay? All right, keep moving. In the 5 previous examples, we had to work with non-uniform magnetic field. In this exercise, for the first time, we are given a uniform field. Okay, uniform means the same or constant. And now also for the first time, we have to deal with a moving frame. The frame here is entering a uniform field, okay, by this direction. The movement of this one is translational. And we can see that firstly when the frame here, the triangle here is totally outside in the exterior of the fin here, there is no magnetic flux. Sorry, there is no magnetic flux. Okay, but when it begins to enter the fins, so you can see that the region inside the fins increases, and so the total magnetic flux will increase also. So we're trying to find that thing. In our exercise here, we knew that the frame here is entering the fin with the speed of v. So this is a magnetic flux, and it depends on the position of the frame. When the frame is totally outside the fin, phi here is 0. When the frame here is totally inside the frame, is inside the magnetic field, the total magnetic flux will be B multiplied to the area of this triangle, which is AH over 2. But please notice that when the frame here is entering the field, so magnetic flux will increase, like I told you. Okay, we return to this one. Because B here is uniform, so it is a constant. And then we can move this one into the exterior of the integration. And the remaining of the integration will be integration of ds, which is s. So finally, we got this. Are you okay? Now I will try to find sh, which is this small triangle. The area of the small triangle here will be the edge here multiplied to the height. Let's suppose that the position of the peak here is h, then the height of the small triangle here is exactly h. Okay, then we have this. This is the area of the small triangle. It is h times height over 2. Now we have to find the length. It is once again a function depending on h. So to find LH here, once again, you can see that we have two similar triangles, the small one and the big one. And we have this. From here, we can find NH. And then, finally, we can find the magnetic flux flowing through the small triangle. It depends on the position of the peak, H. But we cannot stop here because we are not given H, we are given speed V. So we have to change H here into V. The relationship I think is very familiar to you from high school. H is Vt. So you change H here into Vt, you have this. But please keep in mind, like I told you several times, that this relationship exists only when the triangle here is entering the uniform, the uniform magnetic field. When the frame here is totally inside the field, then the magnetic flux here is a constant. And so the first result here is from this moment to this moment. Beyond this moment, the magnetic flux is a constant. Are you okay? This example is very simple. It will be a little more difficult if I change the direction of V. V here is perpendicular to the border. If I change the direction like this, like the entering angle is no longer 90 degrees, it is 60 degrees, for example. So the problem will be a little harder. The problem here will be very difficult if the trajectory of the frame is something like this, you know, it is spiral like this. Can you imagine that case? In that case, the computation will be very complicated. And this is the most difficult case. You can imagine that during the process of entering the frame here, entering the magnetic field here, the frame here is not stay still. It can rotate by itself. So that will be an extremely difficult problem. Are you okay? Any question for this exercise?
I have a question. So when the triangle in the field, so it doesn't depend on when it stay when it movement and when it not movement. It's always the same, right?
Yeah, it is always the same. Because when the frame here is totally inside the field, then its area inside the field is a constant. So, do you have any further question about this? Okay, so I give you a second mid-class exercise. I change the position of the frame. The movement of this frame is the same, like this. I want you to redo this exercise. Are you okay? In the original exercise, the peak here enters first. And in my mid-class exercise here, the edge, the bottom edge, enters firstly the magnetic field. Understand the requirement? Okay, go ahead. I give you 7 minutes for this exercise. Are you alright? We return to this example. In the example number, I don't remember, number 3, right? The frame here is stay still, but now we consider the case in which this one is moving with the speed of v. The movement here is once again translational. So we have to find the total magnetic flux. This is the direction of MF5, and we found 30 minutes ago this result. Okay. Now, unlike the exercise number 3 in this example, B and A, they are no longer constant. They depend on time. To be more specific, this one is A and this one is B. Okay, so the remaining work is very simple. We change B into this and A here into this to have a final result. I want to give some comments on these results. You can see that now the magnetic flux here is no longer constant. It depends on time. And firstly, once again, phi here is proportional to the currents. The greater the current, the stronger the magnetic field, and the bigger the magnetic flux. Okay, but this one depends also on time. When time passes, please keep in mind that in our real physical world, time always increases. So when time increases and v is a constant, you can see that the numerator and the denominator here, they all increase, and finally they will be very, very large. And in that case, the numerator and the denominator will be the same, and this ratio will be 1, and natural logarithm of 1 will be 0. So you can see that when time passes, this magnetic flux will be smaller, smaller, and smaller. Okay, and finally it will come to 0. It can be explained in the other way. When time goes to infinity, this frame will be at infinity. And you know that at infinity, there is nothing, including no magnetic fields, and therefore no magnetic flux. Okay. All right, the last example about the magnetic flux is rotational frame. In exercise number 6 and number 7, we have a translational movement. In this case, we have a rotational movement like this. Our frame here is in the uniform field B, and it is now spinning with a speed, with an angular speed of omega. The frame here is the axis of this frame is perpendicular to the MF5 to the field. So because B here is a constant, then this equation will be B dot S. This is a dot product, and the dot product here, you know, depends on the angle between B and S, which is alpha. But because the frame here is spinning, so alpha is no longer a constant. It depends on time. Firstly, by definition of dot products, we have this. And secondly, we can express this angle as a function of time like this. Okay. So finally, we have the magnetic flux. The magnetic flux here depends also on time, but unlike the exercise number 7, in this exercise, the flux here does not go to 0. It is a sinusoidal function. It is a sine. Okay. Our magnetic flux here has a 0, a maximum and minimum value. The magnetic flux here we obtain its maximum value when the frame here, the surface of the frame here is perpendicular to the field. And phi here will be 0 if the surface of the frame here is parallel to the fins. Any question, guys? Okay, break time, 10 minutes.
Excuse me. Excuse me.
Yes.
Can you explain why VDS and the derivative of VDS equal B dot B multiply
What
S?
are you talking
Yes.
about this?
Yes.
Okay. Firstly, B here is uniform. You see,
Yes.
this one is uniform fin, so we understand that B here is a constant. So this one, because B is a constant, so we can move this one E to the exterior of the integration. So we have this. Okay, and the integration here, because the direction, the frame here is a plate, is a surface, is a planar. So the integration of ds here will be s. There you are. So we have b dot s. Okay.
Yes. Thanks.
Never mind.
Okay.
Okay, keep moving. The last section of this chapter is about magnetic potential. Firstly, we define the scalar magnetic potential. It is Vm. And the definition is for a little strange. Vm is something from which, if we take the gradient, we have MFI. Okay. Please notice that the name is potential, but Vm actually is the current. It is a current difference between 2 points, as you can see in this picture here. Let's suppose that the current here is a 6, the current here is a 10 ampere. So Vm will be 4 amperes. Okay. From this one, we have something else. It is, like I say, a Laplace equation for magnetic fields. Laplacian of Vm is 0. Remember this equation? And finally, besides this definition, we have another definition of Vm. Vm will be the line integral of h dot dn from B to A. This one, you know, is very similar to the potential. The potential is defined as a minus integration of E dot dl. We'll write it here. Remember this one? V is minus E dot dl. It is very similar to what we are talking about here. So the name of Vm is a potential, but remember that is current potential, we can say that. The second definition of this one is vector magnetic potential. Please remember that we have now two things. The first one is Vm, and its name is scalar magnetic potential. Okay. The second one here is a vector magnetic potential. The difference here is scalar and vector, but they are totally different. This one is the definition of A. A is something that from which, if we take the rotation, we have the density, the magnetic field density. The unit of A is Weber per meter. And let me remind you that the unit of V here is ampere. Okay, they share the same path, the same, okay, so they share the same name, magnetic potential, but A and Vm, they are totally different. Second definition of A is this one. This one is the definition here is based mainly on Biot-Savart law. So we can find theoretically A from the distribution of currents in a system. The last section of this chapter is about derivation of magnetic field law, and I'll ask you to read this one by yourself because we don't have much time remaining. And I want to show you a summary about this chapter. In this chapter, firstly, we defined MFI. This is the MFI of a current flowing through a straight wire. Okay. And from the MFI here, if we multiply MFI to the permeability of the environment, we have the magnetic field intensity B. And from B, if we find the total magnetic, if we take the integration of B dot ds, we have the very important quantity in this course. It is a magnetic field, sorry, the magnetic flux. 5 minutes ago, we knew that from H, we can define the scalar magnetic potential, Vm. This is the definition of the scalar magnetic potential. And from B, we define the vector magnetic potential. Okay, so in this chapter we knew 5 very important quantities. They are H, B, phi, Vm, and A. Okay, we finish this chapter here and we move to the next one about force, magnetic force. Give me 1 minute to turn on the next one. All right, the new chapter, this one is about magnetic forces and inductance. Chapter number 9. In a previous chapter, we studied the problem of given the current distribution, we can find the magnetic field's intensity, the magnetic field's density, and the magnetic flux. In this chapter, we study the second problem. It is the force created by the fields, magnetic fields. And also in this chapter, we discuss about the definition and the computation of inductance, the third electrical parameters in a circuit. In this pretty long chapter, we talk about these things from number 1 to number 9. From the definition of EF5, you know EF5 is F over Q, so we can extract the definition of the force the electric field force acting on the charge. Okay, because the Q here is the real number, so the force here is the same direction of EF5. For the magnetic fields, we have another force. Force here is a Q V cross B. And this one is a cross product, so we can determine the direction of the force by applying the right hand rule, as you can see on the screen. And you can see that the force here is perpendicular to both the movement and the field. If we have synthetic fields, including an EF5 and an MF5, then we can find the magnetic flux. We can find the force in this way. To understand better this force, we do the first example in this chapter. We have here a moving charge. It is moving with the speed of 5 times 10 to the power 6 meter per second in this direction. We have to find the force acting on this moving charge in 3 cases: magnetic fields, electric fields, and the combination of 2 fields. The first one is a magnetic force, QVB. To find V, firstly we take its magnitude. It is 5 times 10 to the power 6. Okay, and the unit vector of this one will be the unit vector of the direction vector. And then all you have to do is to find the cross product between V and B. You can use the expansion of the determinants here. And finally, it has this. And then you can find the magnitude of this force. Please notice that from now on, normally the unit of B is millitesla. Okay, look at this. It is millitesla. It is not Tesla. Any question? Well, second exercise here, finding F is very simple because the formula here is very simple. We multiply the magnitude of the moving charge to the given field and here what? Finally, to find the total force here, then please do not add FB to FE, okay, by the magnitude, because they do not have the same direction. To find the FEB, you have to start from the beginning like this, and then you can find the magnitude in this way. Are you okay? All right, the second one. This one was a question in the final examination. This one was a question in the final examination several years ago, and now we're trying to do this. We have here once again a moving charge, and this moving charge experiences no force in a region of both electric fields and magnetic fields. If the magnetic flux is B, then we have to find E. So the total force here is 0 according to the given parameter, given how can I say specification here. There is no force, so the total force here must be 0. So from this you can find very easily E, okay, by finding the cross product between V and B. To compute the cross product, in this case, you should expand the cross product here, like I show you how to do this. Like AX cross AX is 0. AY cross AX will be minus AZ. Okay, and then AX cross AZ will be AY minus AY, and AY cross AZ will be AX, and this is the result. Very simple, right? Okay, now I want you to do the second mid-class exercise here. I change this one into E. And of course, the unit here is volt per meter. And I change this one into B. Please redo this exercise. Understand the question? In the original exercise here, we are given B, we have to find E. Now, if we do the reverse problem, you are given E, you have to find the B. All right? Okay, go ahead. 9 minutes.
Excuse me, can you recommend some advice to solve this problem? Excuse me.
Yes.
Can you give us some hint to solve this problem? Do we need to should we use this formula?
Yeah. So in this case, you are given V, you are given E, and you have to find B. So the best case is that you suppose that B is of BH dot BHAH times BYAY, sorry, plus BYAY plus BZAZ, and then you put into this, and you have two equal vectors. Okay, then set two corresponding components to be the same, and so for that equation you can find the components of B. Okay.
Yes.
This one is a reverse problem, and the reverse problem is always harder, much harder than the forward problem. Okay, I can write here. You can suppose that B is say BH, for example, plus BYAY plus BZAZ, and you put this expression into this. You make the cross products, and you set the two vectors to be the same. And based on that, you can find BH, BY, and BZ. Any question for this? Okay, the next one. We have here a magnetic flux density B And this one you see is a uniform field because this one is constant. We have to find the force acting on a moving charge. The magnitude of speed is 10 to the power 7 meter per second. But the problem is that we change the direction of this movement. We have here 4 cases. The 3 first cases are alongside 3 axes, x, y, and z. The last one is for a specific direction. Firstly, the first question. The most important thing in this kind of exercise is to find the appropriate, how can I say, the appropriate expression of the speed v. For the first case here, the magnitude of v was given. It is 10 to the power 7. Okay, and the direction of v is alongside the x direction. So this one is ax, and the ax cross ax is 0. So we can see that when the movement of the charge is parallel to the field, then there is no force acting on that moving charge. For the second case, all we have to do is to change ax here into ay, because the charge is moving alongside the y direction. Okay, and now we have to care about the magnitude of the charge. This one is an electron, so the charge of an electron is 1.6 times 10 to the power minus 19. And do not forget that we have to add the minus sign here because this one is an electron. Okay, and the ay cross ax is minus az, and ay. The third case, once again, we change ax here into az, and the solution is nearly the same. Okay, for the question B, I think you have to draw a figure like this. The charge is moving on the xy plane, in the xy plane, and alongside the direction having an angle of 45 degrees to the x-axis. Okay, then we have to find the expression of v. Please notice that the length of this vector is 10 to the power 7. So we can project this one onto the x-axis and on the y-axis, and we have this. Are you okay? And finally, all we have to do is make the cross product between the just found v and the given b. Ax cross ax will be 0, and the ay cross ax will be minus az. And finally, and you can see that the force here is perpendicular to the movement and to the field. Now I will change the direction of the movement. I want you to do the next mid-class exercise. Let's suppose that the charge here is moving in the xz plane. And the direction is this, and this angle is 30 degree. Say what? This one is V, and I want you to redo the exercise, the part B of this exercise in 5 minutes. Okay? Go ahead, guys. Ouch. Are you done? This one is not for you, so I skip this. Next one is about force on a differential current element. Differential current element, you understand that this one is a very small portion of a wire carrying a DC current. Okay. And because that very small part of the current carrying DC current, so it has an amount of charges. Let's say that the total amount of charge is dq. So according to Lorentz force, we have this very small force created by the field B acting on a moving charge dq with the speed of v. Okay, and from this we have this formula. If the density, the distribution of current is the current density, so we can change this formula into J cross B dV. And then after several manipulation, we can find the total charge F. This one is the total force of a field P acting on a circuit of L carrying a DC current of I. Okay, and this one is a line integral. Especially if the field is a uniform, is a constant field, then we can change this one into much simpler formula. I think that you knew this formula from high school. Please circle this page number 12. This page is very important in computing the force acting on a frame carrying a DC current I. Okay, I mean this formula, very important. So, do you have any question for this page? Is this okay? All right, to understand this, we do the first example. We have here two wires. They carry two equal but opposite currents, I here and I here. And they are on the xy plane, and the whole system here is in a uniform field. The field here is alongside the x-axis. Okay. Now, because the field here is uniform, so according to the previous page, remember this, when the conductor is straight and it is in a uniform field, then we can apply this formula, I L cross B. So this one is formula of the force acting on the green current. I is I, and B here you see is a BAX because the B is parallel to the x-axis. But the new thing here I want to show you is the expression of L. For N here, firstly, the magnitude of N here is L. And the direction of N here is the direction of the current. The current I here of the green wire is toward the negative direction of the y-axis. So this one is a minus AY. Are you okay with this? And then AY cross AX will be minus AZ, and we have this one. According to the result just found here, we can see that the force, because the B, I, and L, they are all positive. So the force here is alongside the positive direction of AZ, like this, the green force. Okay. Now will be the blue force. This is for the blue force. I and B, they are the same. But now we have to modify L a little. And here, take the magnitude like this one, which is L. But the direction of N here is no longer AY. The direction of N here depends on the direction of the blue current. And you can see that the blue current here is toward the positive direction of the y-axis. So the direction of N here will be AY plus, like this. And AY cross AX will be minus AZ once again. And there you are. And basing on this result, we can see that the direction of FB will be like this, will be downward. Are you okay? Any question? Okay, the last mid-class exercise this morning, I changed the direction of the two currents. I have two currents. The first one here is upwards. The second one here is downwards. I want you to find the two forces acting on these two currents. Okay, go ahead. 3 minutes. It is very simple.
Okay.
Do you have any question? Okay, then
I see the result of a redo exercise.
sorry.
I see the result of it as exercise are the same.
I cannot hear you. Can you say louder?
Can you hear me?
Yeah, now I can hear you.
I see the result of mid-class exercise in here are the same exercise number 1.
Maybe.
But the direction of force.
This one, the n of this one will be L AZ, and this one will be L minus AZ. So I think the result will be different.
Yes. The same magnitude, but
yes, magnitude.
Yeah, and
different direction.
Yes, different. The direction perpendicular the plane
That's
of
right.
current
So
and
we just found forces here. Please notice that the direction of force is always perpendicular to both the current and the field.
Yes.
So in this case, the direction of the two new forces will be alongside the y-axis. It can be positive or negative depending on the direction of currents. All right, so that's all for today. See you next time. Goodbye.
Yes.